We can work out how far away relatively nearby stars are using parallax. But even within the Milky Way, the angle of parallax for more distant stars gets too small for us to use this method. How then do we work out the distance to these more distant objects? It's time to look at standard candles as we watch this space.
3, 2, 1.
Stars.
In astronomy, a standard candle is something with a known brightness or luminosity. This is really important for us as astronomers, as light spreads out as it travels away from stars and is emitted equally in every direction. This means that stars appear fainter the further away they are, such that doubling the distance to a star would make it appear 4 times fainter. So, in terms of what we talked about in the last video, if a standard candle tells us the absolute magnitude of an object, and we can measure the apparent magnitude of it from Earth, then we can work out the distance from us to the object. We can use this equation for this. Regular viewers, yes, we did put this in the last video. Well done for noticing. In this equation, d represents the distance to the star in parsecs, capital M is absolute magnitude, and lowercase m is the apparent magnitude. In this video, we're going to look at 2 different types of standard candles, variable stars and type 1a supernovae. First up, variable stars. Stars are generally kept stable by the balance between the gravitational forces trying to collapse the star inwards and the outwards forces produced from the energy released by nuclear fusion in their cores. This is why they stop collapsing when the core starts fusion and are then stable for such a long time. However, not all stars are so fixed during either their main sequence or giant stage. If you imagine the forces unbalanced, then if the core becomes hotter, it will fuse nuclei at a greater rate. This causes the star to expand, and in the process, cools the core down. This reduces fusion in the core and means that the resultant force causes the star to shrink again. This process repeats, much like the oscillations on this mass spring system. As the star expands and contracts, cools down and heats up, it will go through a repetitive cycle of changing intensity and surface temperature too, which can impact the colour of the star. The most famous type of variable stars are Cepheid variables. The first of these to be identified, and the origin for the name, was Delta Cephei in the constellation Cepheus. It was discovered to have predictable periodicity by amateur astronomer John Goodrick, aged just 19 in 1784. However, it wasn't until the early 1900s that Henrietta Swan Leavitt discovered the link between the time period of these fluctuations and the luminosity of Cepheid variable stars. This period luminosity relation, sometimes known as the Leavitt law, allowed astronomers of the era to work out how far away more distant objects were when parallax would not be an effective technique. The most famous of these was Edwin Hubble, who used Cepheid variables to work out the distance to other galaxies and prove that the universe existed on a much larger scale than previously thought. If you want to know more about the history of this, then you can check out our video on why we call galaxies nebulae until around 100 years ago. To make matters slightly more complicated, Cepheids are not the only type of variable star, and not the only one that can be used as a standard candle. Our Lyrae stars have a shorter time period for their oscillations, usually 2 days or less, and have a fairly fixed brightness range. This means that astronomers need to be careful to identify which type of star they're looking at before using it as a standard candle. These variable stars work out to a certain distance, but if we want to work out how far away more distant galaxies are, then we will need to look at something slightly brighter, type 1a supernova. These supernovae form in a different way to the supernovae you may have come across before, and only occur in a very specific setup. A binary system consisting of a white dwarf and another star, typically a giant. As the two stars orbit each other, the white dwarf can accrete or pull in mass from the other star. This causes the white dwarf to grow, heading towards the Chandrasekhar limit, which at about 1.4 solar masses is the largest mass that a white dwarf can be. The white dwarf never quite reaches the Chandrasekhar limit though, as it begins to fuse carbon and oxygen in its core. This rapidly increases the temperature in the core of the white dwarf, initiating a supernova phase, which will release around 10 to the 44 joules in a matter of only a few seconds. This is similar to the amount of energy that has and will be released by the Sun in its entire main sequence phase, just to put those numbers into context. Because this triggers at the same mass for each Type 1a supernova, that means that every single one of them reach the same peak brightness. As we can see from the data here, collected from a number of Type 1a supernovae, they all reach an absolute magnitude of -19.3 at their brightest. As an aside, note how the timescale has been set to 0 when the peak occurs. The reason for this is that not all supernovae are noticed at exactly the same point. If the time started from when they were first detected, then their peaks would not be synchronized. As the peak magnitude is so bright, this means that Type 1a supernovae can be used as standard candles over incredibly long distances. They have been even useful in helping to determine the expansion rate of the universe, including the discovery that the expansion has been accelerating. That is a story for another video though. Next week we'll be taking our first look at how we locate stars in the sky by looking at the altitude and azimuth coordinate system. Until next time, feel free to take a look at one of our previous videos, perhaps this one. Also, like this video if you enjoyed it, subscribe to the channel if you haven't already, and until next time, please continue to watch this space. Thank you.